start with our next revision for the final part of the gravitation. So again, we're gonna review all the formulas are in this chapter. Number one, we introduce the concept of free fall, which has the value of g 9.81 meter per second squared. So everything that fall due to gravitational force only. That means the air resistance must be neglected. Then all of that object will fall with the same acceleration, 9.81 meter per second squared, also known as the gravitational acceleration. So this case is only for on the Earth. The situation on the Earth. If the situation on the Moon, then it has a different gravitational acceleration value. Next, we learn about weight. So weight is actually the gravitational force. So it has the formula of mg. Okay, W equal to mg, where g here is actually 9.81 Newton per kilogram. So this is the gravitational field strength on the Earth. So it has a different values if we situated at different location, but the magnitude are the same between the gravitational acceleration and the gravitational field strength. The unit are different. 3, we learn about Newton Universal Law of Gravitation. So the formula is big G, big M, small m, r square. We introduce the gravitational constant 6.67 times 10 to the negative 11 Newton m square kilogram negative 2. So this formula here valid for everywhere, for every object that has mass and everywhere in the universe. Doesn't mean that it has to work on the Earth. It can work on to Jupiter, Moon, Saturn, or any Sun even. Okay. Number 4, we learn about centripetal force. Oh, not centripetal force. We learn about gravitational acceleration everywhere. Okay, how about gravitational acceleration everywhere? The formula. So G equal to big G, big M, R squared. So this formula here can be used everywhere as well, not on the Earth only. So number 5, centripetal force, mv squared over r. So this centripetal force here only equals to gravitational force if we don't have rope attached to that object that move in circular motion. So for example, if a moon that rotates and revolve around the Earth, then that means that's the uniform circular motion, that there don't have any ropes that ties between the moon and the Earth. That means the centripetal force is the same as the gravitational force, because the centripetal force always shows the direction towards the center of the rotation, in this case the Earth. And also the gravitational force acted on the moon by the Earth also directed towards the Earth. So basically they have the same magnitude, the centripetal force and the gravitational force. Number 6 is the centripetal acceleration, v square over r. So number 7 is the mass of sun or planets, 4 pi square r cube over gt square. Okay. Number 8 is the Kepler's third law. P square equal to 4 pi square over gm r cube. Okay. So number 9 is the Kepler's third law ratio form. R1 cube, R2 cube. So this is if involve something with around something. For example, a sun and the Earth. So we want to calculate the orbital period between the sun and Earth. this formula here, the ratio is between Earth and other planets such as Venus, Mercury, etc. etc. So comparing the orbital periods between two planets or two satellites. This one between planets and sun, or a satellite and planet, Earth and moon. So you have to use the correct formula. Number 10 is the linear speed of satellite. Linear speed square root gm over r. So this is the linear speed of satellite. So that's mean we have Earth and moon that already outside of the Earth, that already rotate around the Earth, the revolve around the Earth. So the velocity here, the linear speed, is this formula over here. Number 11 is the gravitational potential energy, negative Gm over r. And number 12 is the escape velocity. It has the value square root of 2 gm over r. So this one situation here is the object still inside on the Earth need to escape from the Earth and rotate around the Earth. So before it escape from the Earth gravitational field, and before it move around the Earth, so that it needs escape to achieve escape velocity first, which is this formula here, a value of 2 larger than the value of the linear speed, because the gravitational force is stronger nearer the planet. Okay, now we're ready to solve some problems. Okay, linear speed on circular method. The hammer with mass 6 kg needs constant speed 20 meters per second to launch with radius rotation 1.5 meters. Calculate centripetal force acting on the hammer. So centripetal force, the formula is mv squared over r. So let's check if we have all the needed parameters. Mass, we have mass. Speed or velocity we have, and r, the radius also we have. So let's just plug in like usual, 20 squared over 1.5. So plug in that into our calculator. 6 times 20 squared divided by 1.5, we got 1,600 Newton. Okay. Number 2, a string with length 0.5 meter can withstand maximum force 1,200 Newton used to rotate a ball with mass 20 kg with constant speed 5 meters per second. Is the string snaps? That means that we have to find the centripetal force exerted on the spring and compare it with the maximum force over here. So same formula, mv squared over r, m is 20, v is 5 squared, r is 0.5. So if we calculate that in calculator, we got 1,000 Newton. Since 1,000 Newton is less than 1,200 Newton, so the string does not snap. Not snap. Okay, safe. That's what I mean. Okay, let's move on to Kepler's law. State Kepler's first law. So basically, Kepler's first law is also known as the orbit law, or the law of orbit. Sorry, law of orbit. Law of orbit. So it states the shape of the orbit of the planet. So the planet have elliptical shape of orbit where the sun is at one of the focus, one of the cosine. Okay, basically what it states that if we have elliptical shape, this is the planet, and then every ellipse has two foci, two focus point. So the sun could be here or here. Either way, it's just the same because it's symmetry. But if we assume the sun over here, then that means the sun is only at one focus, not two at the same time. So if we have two at the same time, we have a bi-star system, which is also exists in the nature, but it's not in the solar system that we know. Okay. State Kepler's second law. Kepler's second law is about law of area. So it states that the planets swap equal areas at equal t times period at equal periods. Equal period of time. That's period of time. That's more period. So what is stated that what is really mean if you have the sun over here and then the planet over here. So the planet over here and then the planet over here and also this planet over here and then this planet over here. So basically these two areas over here and these two areas over here are the same areas. Just imagine that this is a big pizza, this is a longer pizza, but has the same amount of meat or chicken on it. Okay, basically they have the same areas. But it's stated that if the planet move swept what the law says swept an area, it will cover an area with this amount of time. So that means if the planet also cover the same area over here, it will also cover the same amount of time as well. So what it means that this distance over here, this displacement over here is longer than this displacement over here. That means that if both has the same amount of time travel, that means this one must be at a higher velocity, moving in higher velocity compared to this one. So what we can say as well that the planets when approaching nearer the sun, then the planet will move at higher velocity. If the planet is further from the sun, then the planet is moving with lower velocity. So that's what it says as well. Okay, states Kepler's third law. So Kepler's third law have a formula. Basically, it says that the square orbital period is directly proportional to the cube of orbital radius. Okay. So Kepler's third law, also known as law of period. Okay. The square orbital period is directly proportional to the cube of orbital radius. So the formula is actually look like this. R cube. So we say that the relationship between this t square and r cube are directly proportional because this value over here in the bracket is actually a constant. If we have if the planets are situated in the same solar system or the same star, it should be M over here. Okay, that's all the Kepler's law. Let's move on to number 4. The moon with orbital radius 384,000 kilometers takes 27 days to complete the orbiting of the Earth. Okay, determine the period of orbiting for a satellite at height 500 kilometers from the Earth. Okay, so basically this is between two satellites. We compare between two satellites because Moon is also a satellite. It's just a natural satellite. This satellite is here is man-made. So we have two satellites that revolve around the Earth. So that means we have to use the second form, which is the ratio form of the Kepler's law that look like this. Okay, so it asks us to calculate the period. So let's assume that this T1 over here and the R1 over here belong to the satellite at height 500 kilometers, whereas the two T2 and R2 over here belong to the moon. So if we want to find the T1, then we can rearrange it like this. R1 3, R2 3 times T2 square. So let's plug in all the values. R1 is the satellite, 500. R2 is the moon. So in this case, we don't need to convert the units because both R1 and R2 are the same. So if we have a ratio and both units are the same, then we don't need to convert it to SI unit. But if it involves multiplication, addition, or subtraction, then we need to convert to SI unit. In this case, it only involves with division, then that's okay for non-SI unit as long as the units are the same for both. So the T2 is 27 days. Also here, we don't need to convert it to seconds or something else because it's going to be a very ridiculous numbers. Because 27 days has a lot of seconds in it, we don't need to know that kind of detail. We need, if we want to describe the orbital period for a planet or jet period, it's enough to state it in days. Okay, so if we multiply that, we got T1. If we plug in that into the calculator, 500 divided by 3 is 4,000 times 27. Oh, I forget that we have to cube the 500 and the 4,000. So don't forget about that. We have to cube the number. It's gonna be ridiculously large, but that's okay. And then this 27 here needs to be square. Okay. So we will get a number like this. 1.61 times 10 to the power of negative 6. But this is not the correct answer. We have to square root. So square root 1.61 to 10 of negative 6. We will get 1.27 times 10 to negative 3 days. So again, this is not a very understandable value here. We can just convert it to hours then. By time it's 624, it will become 0.03 hours. Again, if you want to convert it to minute, also can, and it will become times that by 60, 1.83 minutes. This one looks more better. If you want to convert to second, also can, but why we need such a great accuracy if we already understand well in terms of minute and hours. So if you want to leave your answer in days, it also can. It's not that wrong, but it's very weird that the value is -3. That means 0.0000127 days. It's not that understandable. Then we can convert it to hours, but still hours also involve 0.0 something. Then we can just make it minute then. Okay, 1.83 minutes. Also, if you want to convert further to the second, is also okay. It's also acceptable here, but we don't need that much accuracy. So number 5, in our solar system, the Earth takes 365.25 days to orbit the Sun due to the orbital radius 149,600 km from the Sun. From the observation, planet Venus takes 2 to 4 days to orbit the Sun. Calculate the orbital radius of Venus from the Sun. Again, we involve two planets. We need to compare two planets that both revolve around the sun. So again, we have to use the ratio formula. So T1 squared over, so T1 squared over T2 squared equal to R1 cube over R2 cube. Okay. So it wants to calculate Venus, orbital radius of Venus. So let's assume the top one is Venus, the bottom one is Earth. So it wants R1. So if we rearrange that, R1 cube equal to T1 square over T2 square times R2 cube. So let's plug in all the values. Make sure that you do the square. T1 is the Venus, 224 over 365.25, and then you can square it times R2 cube. R2 cube is 149,600 cube. So let's plug in that into our calculator and write our answer here. So our answer is in terms of cube. 4 divided by 365.25 square times 149,600 cube. So you get 1.26 times 10 to the power of 15. So this is not the answer. We have to cube root. The answer, cube root 1.26 times 10 to the power of 15. And then let's answer here, cube root 107.9 107,986. 987, we need to run out of kilometers. Okay. That is the orbital radius of the Venus, which is should be smaller than the Earth. The Earth has 149,600, the Venus 107,987. Why smaller? Because the orbital period is smaller. Because nearer the Sun, so the orbital period is smaller, orbital radius smaller. So our answer is logical. Escape velocity. What is meant by escape velocity? The minimum velocity required to overcome the gravitational force. The minimum is required to overcome the gravitational force of a planet or sun, in order to move to the space, in order to escape to the space. Okay, so as we know, the escape velocity has a formula. VESC equal to the square root 2gm over r. So why we don't use this formula to make a definition for escape velocity? The answer is the same as why we don't use formula for the definition of force. It's quite the same because velocity here is very specific. Velocity has a formula, displacement over time, so it's just rate of change, rate of displacement. But this escape velocity here is also have the term velocity here. That means it's still displacement over time, which is this value over here. but it's very specific. It says that the escape velocity. Specific like weight is type of force, but it's specific to the gravitational force acted on an object. Or the buoyant force is very specific. It's the type of force. It's specific when the object immersed on a fluid, the upward force exerted on the object is called buoyant force. So in this case, the escape velocity is type of velocity, but it's very specific to gravitational force. So we can make another definition that's more specific towards the terms here. Okay, number two. So that before we move on, I want to add some. We don't need to use this formula to define escape velocity because this formula comes from derivation from other formulas. That's what I mean. If the formula is come from other formula, then we cannot use it as our definition. So what are the formula that don't come from the derivation for our formula? Such as the velocity itself, s over t, distance over time. So distance over time is, or displacement over time, is not come from any other formula. It's just that formula. We define it like that. We define the velocity is must have displacement, must have time. Okay. Then the rate of displacement is the velocity. Same with acceleration, must have final velocity, must have initial velocity, must have time. Then we can calculate the acceleration, the rate change of velocity. But if we have F equal to ma, F equal to ma comes from F equal to mv minus mu over t. So there is another formula, and that another formula as well comes from the Newton's second law. So it has a very a long path of formulas. That means we cannot use the formula to define the terms. Same like escape velocity here. How we going to derive it? We equal the gravitational potential energy with the kinetic energy. So two different formulas that we combine together will become escape velocity. That means we're going to use it to make a definition. As simple as that. So number two, given all the values, calculate the escape velocity to escape from the Earth. So V ESC equal to square root of 2gm over r. So let's plug in all the values. So 2, 6.67 times 10 to the negative 11. The mass 5.97 times 10 to the power 24. R radius 6.37 times 10 to the power of 6. Make sure that you square root at the end. Do not put the square root in your calculator yet. You do the square root as the final step. 2, 6.67 e negative 11 times 5.97 e to the 24 divided by 6.37 to the power of 6 square root become 11,000. So 11,000 11,181.38 meter per second. Okay. Or you can say 11182. Or 11181. Sorry. Or 11181.4. It's okay. Okay, number 3, a rocket with speed 5,500 meter per second can be used to escape from planet Mars. And the same rocket can be used to escape from Venus. Okay. So this is the speed. So that we need to calculate the escape velocity for Venus. Square root 2 gm over r equal to 2, 6.67 times 10 to the negative 11. The mass of Venus is 4 0.87 times 10 to the power 24 over 6.05 times 10 to the power 6 square root it all. So we get, make sure that you do the square root at the final step. 6. 10,000 is 60.5 meter per second. So when we compare these two velocity here, these two speed here, since this is bigger than 5500, so it cannot escape from Venus. It must have a larger value than the 10,362.5 meter per second. Okay, the final question for today. The arm hits a ball upward with velocity 2.5 kilometer per second. What will happen to the ball after a few seconds? So this is actually 2,500 meter per second. So our escape velocity for the Earth, we already calculated before. Escape velocity for the Earth, because we assume that this ball here, Adham, is on the Earth. So the escape velocity from the Earth is 11,181.38 meter per second. Okay, since the value is smaller than the escape velocity, so what happened to the ball? The ball will fall down. The ball will free fall after few seconds. Free fall is the correct term here because it's due to gravitational force. If the ball were hit on the surface of the moon, what will happen to the ball? Okay, when we assume that the first question A, we assume that Adham on the Earth. Now we assume that Adham is on the moon. So the moon, we have to calculate the escape velocity of the moon first. 2gm over r. So 6.67 times 10 to the negative 11. Mass of the moon is 7.34 times 1022 divided by 1738000. Make sure that you square root at the end of your calculation. Divided by 1738000 square root 2373.56 meter per second. So if you compare 2,500 with 2373.56, 2,500 is larger. Thus, the ball can escape from the moon and revolve. So we can say that escape from the moon and orbits the moon with linear speed. With constant linear speed. Okay. I think that's all for today. Let's before we end, let's review all of the formulas. Okay. So here the formulas. Free fall. So free fall, the condition to achieve is if the object falls due to gravitational force only. There is no air resistance. That means the object must fall in vacuum or the object must be massive. That's two conditions needed, or either one. So if the object falls in free fall, then it has the same acceleration, 9.81 meter per second square. That means the object will fall at the same time with increasing velocity, regardless of the mass and the shape of the object. So number two, weight. How to calculate weight? Weight is actually the gravitational force, but the terms weight only used when we measure the we measure it by using instruments, so that we call it weight. So we know that the weight is also equal to the gravitational force acted on an object. The formula is W equal to mg, but g here has the same value as the gravitational acceleration, 9.81, but has different unit, Newton per kilogram is different. So this term here we call it gravitational strength only on Earth. If it is on at other place, then we have different values. So next we learn about Newton's Universal Law of Gravitation. Basically, it can be used everywhere. Fg equal to big G, big M, small m over R squared. So directly proportional to the product of the two masses, inversely proportional to the square distance between the centers of the two objects. So we introduce another gravitational constant called the gravitational constant, 6.67 times 10 to the negative 11 Newton meter square kilogram negative 2. And then we derive formula for gravitational acceleration that works everywhere. Big G, big M over R squared. Centripetal force has two situations. First one, if it has rope attached to an object. The second one doesn't have rope. If it has rope, it's called centripetal force. If it doesn't have rope, the centripetal force is actually the same as gravitational. Okay, centripetal acceleration, mass of planet or sun. How do you want to calculate that? Make sure that we have the orbital period and the orbital radius. So then we can calculate the mass. The Kepler's third law, this case only used when something revolves something. One object revolves one object. Okay. Number 9, the ratio form of the Kepler's third law we use if two objects revolve the same thing. So we want to compare between the two objects. Okay. Number 10, the linear speed. The formula for the linear speed. This is used when the case that the object is already outside of the Earth or the planet or the sun that constantly revolve around that point, already outside of the gravitational influence. So that means it already moved in uniform circular motion. So we can use the linear speed formula. Number 11 is the gravitational potential energy. We must have negative. 12, the escape velocity. This case is used when the object is still on the Earth or still on the planet or the sun, not in the space yet, not revolve around the planet or the sun yet. So basically, we want to achieve a certain value of velocity first. We call it the escape velocity before it can move around the Earth or sun. So that's all for me for today. Hopefully that we can see each other soon. So hopefully that you understand all the formula, when to use it, what kind of the constant needed, what kind of information needed, um, the correct units, and such and what kind of situations that specifically needed for that kind of formula. So hopefully you understand all of the contents presented here. If you have some questions, feel free to message me. Okay, thank you.